Before we formally begin today's session, may I request everyone to join us in a brief moment of silence. Thank you. Good morning, everyone, and a warm welcome to the inaugural ceremony of CSMA 2026, the International Conference on Complex Systems Modeling, Analysis and Applications, formerly known as IC2 SMA2. To begin this auspicious occasion, I request everyone to join us in the inaugural prayer, seeking blessings for the successful conduct of this conference.
O Lord my God, when I in awesome wonder consider all the works thy hand hath made, I see the stars, I hear the rolling thunder, thine path throughout the universe displayed. Then sings my soul, my Savior God, to thee. How great thou art, how great thou art. Then sings my soul, my Savior God, to thee. How great thou art, how great thou art.
Before we move forward with the inaugural ceremony today, we would like to share a glimpse of our university with our esteemed guests.
Christ University Pune Lavasa Campus is nestled in a picturesque location surrounded by nature, providing students with a peaceful and inspiring learning environment. It's a vibrant hub of analytics where students can explore the exciting world of science, arts, commerce, law, business, and management.
At Christ Lavasa, the residential campus of Christ University, education is more than just textbooks and lectures. It's about gaining real-world experience and developing the skills you need to succeed in your future career through learner-centric approaches.
Here, you get to work on projects and collaborate with your peers, gaining valuable experience in teamwork and communication. Get ready to tackle the real world head-on. At Christ University, we believe in preparing our students for the challenges and opportunities of the future. From hands-on learning experiences to cutting-edge research projects, we equip you with the necessary tools and resources to make a real impact and leave a lasting mark. Students thrive in a vibrant event culture that celebrates diversity and talent. We pride ourselves on creating a friendly and inclusive environment where you make lifelong bonds and memories.
If you come to this hub of analytics with dreams and aspirations, we shall provide you with every single resource, guidance, and platform to reach there.
At Christ Lavasa, students not only have access to top-notch facilities, but also have the opportunity to engage in a wide range of activities. Allowing them to develop important skills, broaden their horizons, and create lifelong memories. Discover endless possibilities at Christ University Pune Lavasa Campus, the hub of analytics.
In Indian tradition, lighting of the lamp symbolizes the dispelling of darkness and the triumph of knowledge, wisdom, and hope. With that spirit, I invite our Dean and Director, Dr. Father Lijo Thomas, our Academic Coordinator, Father Justin, Dr. Jibril Jose, our Associate Dean, our esteemed guests, Dr. Hiroki Sayama, Dr. Deepak Dhar, Dr. Anirban Chakraborti, Dr. Clemens Arts, Dr. Manjri Sharma, and Dr. Preeti N. on the stage for the lighting of the lamp. Moving forward to formally welcome our distinguished guests and participants, I would like to invite on stage Dr. Manjri Sharma, the head of the Department for Commerce at Christ University, Lavasa, a keen researcher herself with more than 15 years of global experience in academics and several research papers to her credit. Ma'am, I kindly request you to take the stage.
Thank you, Sukhbir. A very good morning to each and everyone present here. It is my pleasure to warmly welcome you all, our distinguished speakers, colleagues, research scholars, and my dear students, to CSMA 2026, International Conference on Complex Systems Modeling, Analysis, and Applications, hosted at Christ deemed to be University, Pune Lavasa Campus, in collaboration with Binghamton University, State University of New York. At the outset, I extend our respectful regards to our patrons, Dr. Father Joe C.C., Vice Chancellor, Dr. Father Viju, Pro Vice Chancellor, whose encouragement continues to support academic initiatives across the university. We are honored to have with us our campus Dean and Director and the General Chair of the conference, Dr. Father Lijo Thomas. I also greet Father Justin P. Verghese, Academic Coordinator of the campus and General Co-Chair of the conference, along with Dr. Jibril Jose and Dr. Parmeshwaran, Associate Deans and General Co-Chairs, whose guidance shapes both the academic and organizational direction of this conference. We are privileged to welcome our collaborating partner and technical program chair, Dr. Hiroki Sayama, from Binghamton University, whose continued associations reflects the strength of this international partnership. We are honored by the presence of our distinguished speakers and guests, Padma Bhushan Professor Deepak Dhar, Professor Anirban Chakraborti, and Professor Dr. Clements, whose work reminds us that understanding today's world requires crossing disciplinary boundaries. I also acknowledge Dr. Preeti N., Technical Program Chair and Head for the Center for Research, Christ University, for her leadership in shaping this conference. I would like to further acknowledge the efforts of our organizing chairs and welcome Dr. Blesson Varghese, City Campus Coordinator, myself, Dr. David, who is a Department Coordinator at Department of Commerce, Dr. Mahesh Kumar T., Ms. Preeti Jain, and Mr. Alvin Jose. Along with the Technical Program Committee members, publicity team, contributions together make this conference possible. In recent years, we have increasingly witnessed how quickly local actions turn into global consequences in markets, technology, and society. We no longer study isolated problems. We study interconnected behavior. This is why complex systems thinking is no longer a specialized approach. It has become an essential lens, not to eliminate uncertainty, but to understand patterns within it and make responsible decisions despite complexity. At Christ University, Pune Lavasa Campus, we are consciously nurturing an academic environment where analytics, economics, management, and computational thinking intersect. Hosting CSMA 2026 for the second time reflects this direction and our continuing collaboration with Binghamton University. Over the next 2 days, I hope the most valuable outcomes will not only be the papers presented, but the conversations initiated. Because meaningful research often begins with a thoughtful question rather than a patterned answer. With this, I warmly welcome you all to CSMA 2026 and wish you a stimulating and engaging conference. Thank you.
Thank you, Dr. Manjri Sharma, for this warm welcome. Now moving forward, I would like to invite on stage Dr. Preeti N., the Technical Program Chair of CSMA 2026, to address the gathering. Dr. Preeti N. is a distinguished academic and researcher with nearly 2 decades of experience in teaching and research. She has authored several publications in international journals and has made noteworthy contribution to interdisciplinary research. Ma'am, I request you to kindly take the stage and share the conference details with our audience.
Thank you, Shubhir. A very good morning to one and all. Respected Father Lijo Thomas and esteemed Father Justin P. Varghese, Christ University, Pune Lavasa Campus. Distinguished chief guest, eminent speakers, associate dean, faculty members, researchers, scholars, and my dear students. It is with immense pleasure and profound academic pride I welcome you all to the International Conference on Complex System Modeling Analysis and Application CSMA 2026, jointly organized by Christ deemed to be University Pune Lavasa Campus, India, and Binghamton University, State University of New York, USA. CSMA 2026 is a global forum dedicated to advancing complex system research and interdisciplinary collaboration to address critical real-world challenges through rigorous and innovative scholarship. As technical program chair, it has been a privilege to work along Dr. Hiroki Sayama, whose distinguished expertise and global leadership in complex system research have significantly strengthened the scientific depth and international stature of CSMA 2026. This year, after a rigorous and comprehensive peer review process, only 30 high-quality research papers were selected for presentation. This careful selection reflects our unwavering commitment to maintain the highest academic standards. The selected contribution demonstrate methodological strength, innovation, and interdisciplinary relevance. We are proud to host participants from distinguished institutions across India and the world, including Binghamton University, University of California, Berkeley, Technical University of Denmark, University of Rhode Island, University of Fraser Valley, Northern West University, and Arab Open University, along with premium Indian institutions such as IMD, Pune, VIT Pune, and Christ University. The diversity and academic excellence represented here reflects the growing global impact of CSMA. We are gratefully acknowledge the generous support of Anushandan National Research Fund, ANRF, which has funded this conference with 2,50,000 and endorsement of national relevance and scholarly standing of this initiative. We are deeply honored by the presence of distinguished chief guests and privileged to be inspired by keynote address from eminent scholars such as Padma Bhushan awardee Dr. Deepak Dhar and Dr. Anirban Chakraborti, professor at JNU and fellow of the World Academy of Sciences. Their pioneering contribution enriched this conference with intellectual depth and global perspective. CSMA 2026 is not merely a conference, it is the convergence of ideas, innovation, and global collaboration. It is a place where theory meets applications, where discipline intersects, and where knowledge transforms into impact. As we encourage in discussion over the coming session, let us remember the true purpose of research extends beyond publications. It lies in its power to influence thoughts, inform policy, inspire innovation, and serve society. May the idea exchange here ignite new collaboration, spark transformative research, and build endorsing international partnership. I sincerely thank our Honorable Director, Dr. Father Lijo Thomas, for his visionary leadership and for his unwavering support in making CSMA 2026 possible. And Father Justin P. Varghese for his invaluable guidance and institutional support in enriching the successful conduct of this international conference. Together, let us advance the science of complexity and contribute to a more robust, informed, and sustainable world. Thank you all, and I wish CSMA 2026 a grand and resounding success. Thank you.
Thank you, ma'am, for sharing these details with us. To take this inaugural session forward, it is my privilege to invite Dr. Father Lijo Thomas, Director and Dean of Christ University, Pune Lavasa Campus. An accomplished academic leader and researcher, Dr. Father Lijo Thomas plays a pivotal role in shaping the academics and institutional growth of this campus. His academic journey includes significant international experience in the United States, where he served as a researcher and adjunct professor at the University of Louisiana, engaging in teaching, research, and student mentoring. As director of Pune Lavasa Campus, he continues to promote a vibrant research culture, interdisciplinary learning, and meaningful academic collaboration. As the general chair of CSMA 2026, he supports initiative that upholds academic excellence and foster global scholarly dialogue. Father, I request you to kindly take the stage and address the gathering.
Good morning. Honorable Chief Guest, Padma Bhushan, Dr. Deepak Dhar, Professor Anirban Chakraborti, Professor Dr. Hiroki Sayama, and Dr. Clements, Associate Deans, Dr. Manjari, Head of the Department, and one of the two key pillars of this conference, beginning of this conference, is Dr. Hiroki and Dr. Preeti from Christ University. This whole conference evolved from their conversation a couple of years back. And respected faculty members, presenters, speakers, and my dear students, as I am standing before you to inaugurate this wonderful conference, which is one of the need of the time, and which is something is thriving in terms of many of our decision making. I'm truly humbled to stand in front of all these dignitaries and stalwarts in the complex systems and modeling. And we are truly blessed. I'm talking on behalf of all of us. I'm coming from a slightly different background, social psychology background. Many of you are also not from that, but it's for all of us, learning from all these stalwarts and wisdoms and expertise in this area, which is going to be one of the key things for our future decisions, even our daily decisions. I will explain how and why, which I learned. Yesterday, I was asking a couple of the students who are the organizers, and asked them, I'm coming from social psychology background or maybe psychology background. I do not know much about this complex system and your computer science, these things. So you have to tell me what I should speak and what is it for a common person. And some of the students actually gave me some good examples. So Father, things are happening like in our life. We create patterns. There are interconnected patterns of our behavior. I think she also explained to me with my psychology, because that's what social psychology is very much connected to complex system modeling, because we can really connect it to our behavior. So these patterns of behavior can predict what it would be in the future, after 1 month or 2 months or 3 months. So I was so happy to hear that, because this is that is what we are actually doing on this campus. Anytime I make mistakes, you make mistakes, we forgive, right? But if the mistakes are continuous and consistent, these are all interconnected components, instances. That should indicate something else that should be addressed seriously. One time mistake, forget about it. Second time mistake, we all do it. Third time, fourth time, fifth time, sixth time, seventh time, we need to pay attention on that. If not, the result will be this or this, right? So here, if we can twist that decision making into our behavior, that's one of the reasons why we have building an extracurricular transcript on this campus. And we are the only one in the country, and only one in the entire University of Christ University. We are the only one we can do, because we are compared to a smaller number. We can observe it's a residential campus. So all of our behavior, including mine, it's actually mapped what we are doing. Your attendance in your club, activities and everything, it's called Edu Track. That's the latest name given, because we started with a new app called Ment Easy, which we found that it's come a lot of limitations. So we have coming up with a new tracking mechanism what you are all doing. Everybody is doing into sports and cultural activities, that thing, this thing. Some people are consistently absent. Some people are consistently absent in Mondays. Some people are consistently absent on Fridays. Or these things are indicators. If 15 Fridays are absent, those are connected components. Dr. Hiroki, you should correct me if that is what I'm directly, I'm trying to communicate was based on the social psychology background and how I understand complex system. Of course, experts will come and correct it. But this is very important for our life. And this is very important for our future and our daily life. And especially when we are living in a group, in social settings, how and move forward and proceed with our decision. That will decide our future and growth and successes or failure. So, my dear students, I think this conference, CSMA, is actually a very good thing for not only in academic line, but also in our daily life decision making and daily life behavior patterns to construct and deconstruct and reconstruct in our life. So I hope this conference will help all of us, both in academic as well as in our daily behavior decision makings in our future, for our future successful journey. And wish all the organizers for this wonderful organizing pattern. After listening that Dr. Manjari was listing out all the names, again, those are also components. These components, I could easily predict that this is going to be the result. See, certain other components are coming, we can predict that this is not going to happen this excellent, right? So the components coming together, definitely we can predict how the event would be, how the outcome would be. So thank you very much, entire team, the organizers, the whole list you have seen. At top level is ornamental, forget about that. Starting about that, from that technical chairs onwards, they are the one actually worked so hard. And much more than that, so many pictures you haven't seen, they are the one actual true engine, the fuel. They burned late night work. I have seen for the last 2-3 weeks, they were leaving around 10 o'clock, 11 o'clock, 12 o'clock, late night. Sometimes they were not eating something. I asked her, did you eat anything? No, we will finish it and go and eat. So that much of work you have done, and I appreciate all the organizers, and I hope the participants will definitely make the benefit out of it, and looking forward to have that growth and transformation in our through this conference, in our decision making and in our learning. Wish you all the best. Officially, with all of your permission, officially inaugurate CSMA 2026 Open. Thank you.
Thank you, Father, for addressing our audience and throwing light on how intertwined now the behavioral pattern and complex systems have become. To move further, I would also like to invite Dr. Jibril Jose, our Associate Dean at Christ University, Pune Lavasa Campus, a dynamic leader and researcher with a rich global experience, to address today's gathering.
Whenever there's a conference of this nature, the conversations which happen can be quite interesting. And if you take time out and discuss what is complex systems, what is the impact of complex systems, many times we think we can change the pattern of society, we can change how Lavasa will be. Father and I, we think of rules and regulations, and we think by putting them down, things will emerge, patterns will come out. But many times it's very difficult. The sun may be there, the gravity may be there, but the weather is so unpredictable. Especially if you come in a rainy season in Lavasa, you will see the storm clouds, the rain, and you will be sure tomorrow it will rain and it will be a sunny day. And you want a convocation to happen and you don't want rain to happen, and then maybe rain will happen. So these are the small things which happen. The patterns emerge. Maybe one of you will start a club and maybe 100 people will join that club and suddenly there's a change in the way college does. Maybe one student is suspended, dismissed for substance abuse sometimes. It's quite sad. Now, should we let the child continue? Should we dismiss the child? It's such a crucial decision. But it may impact 10 others who are maybe using that substance. It's a serious matter. When we look at systems, there are small things which change. We, as in the molecule in that environment, have a role to play. Maybe we'll inspire somebody else. Maybe we'll be a catalyst for change which will happen. Today, our Vice Chancellor has not joined with us. His mother passed away. And when I was thinking about his mother, who's 88 years old, she's a mother of 2 priests. One is a school principal. The other is the Vice Chancellor of our university. You know, what is the impact she has made? Is it a life she has truly lived? So you may have the whole complex world, but you know what mother is, right? And what mother can mean for each one of us. You all can play a role. We all can play a role which can be much bigger than what we may have potential, what we may imagine to be. Time and again, we find the average student, the weak student of the class, doing great and well in life down the line. What makes that child suddenly achieve that next level? You know, I love coding, I love writing algorithm, genetic algorithm, the Conway's game of life, I remember writing. And sometimes you write these slides, loops, and then the pattern emerges, and you know, we write a program and then the solution comes out and we say, wow, it worked, the evolution algorithm worked. But in the real world, it's much more complicated. When we start doing research, we think we know exactly what we'll do. We start a journey, MSc, you have Chart Ruchira, and you know, down the line, you're publishing a paper today. But what happens with time, we also evolve. We realize what all is involved in the research domain. We understand what research has been done. You know, we think that the Maggie cutlet we created in 2003 was an innovation. Then you Google and check and find in 1990 somebody had made Maggie cutlet. You know, the cutlet which you made, you thought was an original recipe, was being done many years ago. But my children loved that cutlet. They loved that innovation, the research which I did to create that cutlet out of Maggie. What will you innovate? What will you create? What kind of innovations will you bring? The challenge is up to you, to all the students, all the participants. Let's have conversations, get a chance, interact with the people who have come, the guests who have come. Thank you. All the best.
Thank you, sir, for addressing our audience, and I hope everyone will get the opportunity to talk and have conversations with our guests. Moving forward, I would take this opportunity to introduce our distinguished guest and Technical Program Chair of CSMA 2026, Dr. Hiroki Sayama. Professor Hiroki Sayama is a State University of New York Distinguished Professor at the School of System Science and Industrial Engineering, Binghamton University, a widely respected scholar in complex system science. He has served as the director of the Binghamton Center for Collective Dynamics of Complex System, where his work brings together ideas from science, engineering, and social sciences. Under his leadership, Binghamton University is a co-organizer of CSMA 2026, and Professor Sayama serves as the Technical Program Chair, guiding the academic direction of this inaugural edition. His research focuses on understanding how meaningful patterns and collective behavior arise when many individuals or elements interact, with applications that range from natural and engineered systems to human and social settings. Through his teaching, research, and international collaboration, Professor Sayama continues to contribute to the growth of complex system science and to the creation of platforms that encourage open dialogue and shared learning across disciplines. I request Dr. Hiroki Sayama to kindly take the stage and address our gathering.
Good morning. Thank you very much for having me to this wonderful opportunity. Let me correct one thing. I'm not a guest. I'm one of the Christ University faculty member here. So I'm, yeah. I would like to start thanking by thanking the Father Ligio, Father Justin, and especially Dr. Preeti for the amazing effort that made this conference possible. I was initially trying to introduce the basic concept of complex systems, but Father gave us the perfect explanations. I don't have to repeat the same thing. So this conference was initially started with some conversation between Dr. Preeti and me a couple of years ago. Dr. Preeti just suggested maybe we can host a conference. I honestly exploited her offer. Let's do a complex system because that's my research area. Turns out, I now think that that choice was actually the very, very important decision, especially because you see the world is changing and many decision makers, surprisingly, they still use a very linear thinking. Here's a problem, here's a solution, let's apply. And then they believe that the solution can be easily solved by patchy approaches, which is part of the many, many reasons why we face lots of problems. So it's very important to apply complexity science, complexity thinking, system thinking to every aspect of business, policy making, environmental management, any kind of decision making. So that's why it's very important to connect theory and applications through venues like this, and also especially this particular region, South Asia, to India. So we should promote more of the interdisciplinary complex systems type of approaches that combines both the government, public sectors, and industries. So I feel very, very fortunate to have this opportunity serving as part of this initiative. I hope everybody participating in this conference is going to learn a lot and then contribute to the future of our society. Thank you very much.
Thank you, sir, for being an important part of our conference. Moving forward, it is a matter of great honor and privilege to introduce Padma Bhushan Dr. Deepak Dhar. Dr. Deepak Dhar is an internationally respected theoretical physicist and a distinguished professor at the International Center for Theoretical Science, Bangalore, India. He is widely regarded as one of the most influential thinkers in statistical physics and complex systems. His research has helped explain how simple interactions can lead to large and unexpected outcomes, influencing studies across physics, mathematics, and many related fields. The idea developed by Professor Dhar continues to guide research on how complex behavior emerges in both natural and human-made systems. In recognition of his outstanding contributions to science, Professor Dhar has received several major honors, including the Padma Bhushan in 2023, the Boltzmann Medal, and the Shanti Swarup Bhatnagar Prize. He is a fellow of leading science, academics, and remains an inspiring presence in the global research community. Sir, it is my honor to invite you on the stage so that you can address our audience.
Thank you very much. It is very, firstly, I would like to thank the organizers for inviting me here. It's a great honor. The subject of complex systems is, of course, by definition, something for which simple answers cannot be provided. So, you know, if I can find the answer in one sentence or in 1 hour lecture, then the subject was not complex enough to begin with. What I'm saying here is that actually the science of complex systems will not be able to answer completely the subject, but we can certainly provide some better insight into the thing. And what has happened in the past is that there were, you know, traditional universities and there were traditional departments, physics, chemistry, history, geography. And it turns out that in the current setting, these department labels have become a little bit less relevant. And the kind of subjects we deal with, the problems we deal with, typically involve more than one subject or department label. And so these are what has now been called interdisciplinary studies. And complex systems typically are involve 2 or 3 or more of these different traditional departments. And the students, fortunately, are not so, they are not brought up into this straight line thinking that, oh, this is physics, this is chemistry, and they are much more open to ideas. And so I hope that this conference will be useful for you in understanding about the world and leading your life in future as a person, decision maker in the complex world we live in. So with this, I will stop here, and good luck with the conference, and let us hope that it will be useful for all of us.
Thank you, sir, for gracing us with your presence and sharing your valuable insights with us. Moving forward, I would like to introduce our guest, Dr. Anirban Chakraborti, the recipient of the Young Scientist Medal in the year 2009, a professor at School of Computational and Integrative Sciences, Jawaharlal Nehru University, New Delhi, a globally recognized researcher in econophysics, sociophysics, and complex system science. His work is internationally known for applying principles of statistical physics to the analysis of economic and social systems, offering new theoretical frameworks for understanding inequality, market dynamics, and collective behavior. He has made foundational contribution to interdisciplinary research at the interface of physics and economics, and has played a key role in establishing econophysics as a rigorous scientific field. Professor Chakraborti has published extensively in leading international journals and has edited influential volumes on complex system and socioeconomic modeling. With a strong record of international collaboration, academic leadership, and scholarly recognition, his research continues to shape contemporary discourse on complexity-driven approaches to socio-economic analysis. I request our guest, Dr. Anirban Chakraborti, to kindly take the stage.
Good morning, and thank you very much for this wonderful hospitality and warm welcome. I'm honored to be part of this conference, and I'm especially humbled because Professor Deepak Dhar has been my mentor for very long. I was a first-year PhD student when I met him in '99, and our introduction was kind of interesting. I'll share that personal anecdote. So I went to his office. I was returning from a conference in Italy, and so I was visiting Tata Institute of Fundamental Research, where he was a professor. And my supervisor was his very close friend and collaborator. So he said that you're going to TIFR, talk to Deepak. So I said, fine. So I knocked the door, and I started speaking in Bengali. So he said, oh, I am Dhar, but I'm not the Bengali Dhar. Because I assumed that the Dhar title is also in Bengal, and I assumed that he was Bengali. Now, that also happens because you'll find that most of the researchers in physics in the Indian institutes and universities are Bengalis. So they say that you often have to learn the language Bengali if you want to participate in a conference in physics. But it's just a joke. Now, I was very happy to see the emblem of Christ University and the candle burning, and I believe that it's the light of knowledge that we're talking about, which reminds of our very ancient, shloka from Brihadaranyaka Upanishad. I am sure most of you have heard it, right? Asatoma Sadgamaya, Tamasoma Jyotirgamaya, Mrityorma Amritam Gamaya, which means that lead me from unreality to truth or reality. lead me from darkness or ignorance to knowledge or light, and lead me from the world of mortality or attachment towards the world of spirituality. Now, we are scientists by training, and tomorrow I'll be talking about the science, but I wanted to touch upon a very few points which is being very much discussed in this critical juncture. You know, I was in a conference in Delhi. This is a pre-summit to the AI conference, AI summit, which will happen next week. And one of the topics was that, students are afraid, faculties are afraid, how will AI transform our system of education and learning, right? Now, we've already seen, and we were discussing this morning, that the role of teacher is changing. We are no longer the information provider. In fact, you have more information at your fingertips through your Google or ChatGPT, and it gives you much more information than any of us can provide. Now, how does my role change? Okay. Now, these type of questions have been often asked from very long time, and I remember a very nice quotation by the French mathematical physicist Henri Poincaré. So he wrote in 1948 a book called The Value of Science. And he was asking that, what are we actually doing? What are we doing in science? And so we'll talk about the science part tomorrow in my lecture. But he actually said, that the search for truth should be the goal of our activities. It is the sole end worthy of them. Okay? And you will see that is what we are resonating, with this emblem that we are talking about, that, we are searching for truth. As scientists, we try to understand what happens in nature, what is the truth that we are discovering. And Father Lijo Thomas and all are dealing with psychology and what are we dealing inside and what goes on here in the brain, right? Now, you'll see that both are very complex systems, and I was discussing that we are doing experiments with EEG and all to understand how the human brain works, which is one of the most complex objects. You have roughly 100 billion neurons which are connected to each other, and all the complex decisions, critical decisions you're taking is a result of the interactions amongst those neurons. Now, what we will find is that, as Father already mentioned and Professor Deepak Dhar was saying, that in complex systems it's difficult to predict what is going to happen because we are dealing with systems which are interconnected, there are a large number of components, and we don't know what will emerge. And so if I study the behavior of Dr. Mahesh Kumar here, in isolation, I cannot predict the behavior of Hiroki Sayama because we are very distinct individuals. And how they will behave in isolation and collectively also changes. On top of that, I'm meeting him for the first time. I will be a little formal, but as I meet again and again, it will become informal. So the interaction changes. Now that's the example of complex systems. Otherwise, I know that there are 10 to the power of 23 molecules in this glass of water, okay? And good thing is that all the water molecules have same chemical structure, H2O, right? And same physical properties. So I can write an equation of state for this water and tell all about its thermodynamic properties, right? That's what you do in school, in high school. But I can't do the same thing for this room full of people because we are a complex system. Now, what brings me next is a very nice quote from James Gustav Speth. He used to head the United Nations Development Program, UNDP, and he was an advisor to the US government on climate change. And so I wanted to read a quote from him. This was part of an interview which he gave in 2013 to BBC Radio, and it was called Shared Planet, Religion and Nature. So he said that, I used to think the top global environmental problems were biodiversity loss, ecosystem collapse, and climate change. I thought with 30 years of good science, we could address these problems, but I was wrong. The top environmental problems are selfishness, greed, and apathy. And to deal with these, we need a spiritual and cultural transformation. And we scientists don't know how to do that. So that's where I think an institution like Christ University is very important, because along with your knowledge that you get in the classroom, you are also undergoing a spiritual and cultural transformation, which is to make you all think beyond me and myself, or you and yourself. So you'll realize that if I don't think about other people and beyond me and myself, I won't be able to survive. This planet won't survive, right? So we have to become what we call spiritually involved, right? So with these words, I want to thank again all the organizers for their tireless work. It's my first time to Lavasa, and I'm loving the campus. I'm sure you all love the campus as well, and we'll be able to interact in the next 2 days. And if you happen to be in Delhi, I'm in JNU, you're most welcome to come and visit us. We also have a very nice campus close to the airport, and you're always welcome. Thank you very much.
Thank you, sir, for sharing your valuable insights with us. Moving ahead, I would like to invite our Dean and Director, Dr. Father Lijo Thomas, our Associate Dean, Dr. Jibril Jose, to join us on the stage to felicitate our esteemed guests. I would also request Dr. Manjari Sharma and Dr. Preeti N to join us on the stage. I would like to invite our esteemed guest, Dr. Deepak Dhar, to join us on the stage. I request Dr. Father Lijo Thomas to felicitate our guest, Dr. Deepak Dhar. Sir, I would request you to remain on the stage. I would also like to invite Dr. Anirban Chakraborti on the stage. Public Law at Berlin School of Economics and Law on the stage. Thank you to all our dignitaries. To conclude today's inaugural session, now I would like to invite Ms. Priti Jain, Assistant Professor at Christ University, Pune Lavasa, and a key member of the Organizing Committee of CSMA 2026 to deliver the vote of thanks.
Respected dignitaries, faculties, and my dear students, a very good morning to everyone. It's my privilege to propose vote of thanks for the inauguration of International Conference on Complex System Modeling, Analysis and Application, CSMA 2026. An event of this importance is never the work of one person. It is a result of strong leadership, academic dedication, and teamwork. I would like to sincerely thank our Honorable Director and Dean, Dr. Father Lijo Thomas, for his vision and continuous support. Because of his encouragement, we are able to host an international conference of this level and importance. My heartfelt thanks to Father Justin P. Verghese for his guidance and support in strengthening the academic environment that makes such initiative possible. I would like to express my deep gratitude to our esteemed keynote speakers, Padma Bhushan Awardee, Dr. Deepak Dhar and Dr. Anirban Chakraborti, for your valuable insights. Remind us that research goes beyond academics and has the power to influence society and shape the future. My sincere appreciation to Dr. Preeti N., our Technical Program Chair, and Dr. Hiroki Sayama for their leadership and careful planning in organizing this conference with high academic standards and global relevance. Thank you, Dr. Clement sir, for joining us today. I also thank the Anusandhan National Research Foundation for their generous financial support, which has greatly contributed to making this conference possible. I extend my sincere thanks to our HOD, Dr. Manjari Sharma, Associate Deans Dr. Jibril Jose and Dr. Parameswaran S., Department Coordinator Dr. David Joseph, respected other department heads, faculty members, the organizing committee, and the teaching and non-teaching staff who work tirelessly behind the scenes to ensure the smooth inauguration. A special thanks to our student volunteers and core committee members. Your energy, commitment, and professionalism are truly appreciated. Finally, I warmly thank all the delegates, researchers, and participants who have joined us from different institutions and countries. Your presence makes this conference truly international and meaningful. As CSMA 2026 continues, may the discussion lead to new ideas, collaborations, and valuable contributions in the field of complex system. With sincere gratitude, I conclude. Thank you, everyone.
Thank you, ma'am, for your closing remarks and summing up this inaugural session today. Before we formally end today's session, I would request everyone to kindly rise for the university anthem. Distinguished Professor at the International Center for Theoretical Science, Bangalore, and an internationally respected theoretical physicist known for his pioneering contribution to statistical physics and complex system. Sir, I would like to invite you on the stage and deliver your keynote address.
Just about complex systems. It is a big subject, and I just made some small choice, and the aim is to show that you can model different complex systems, and in the process of modeling there is always necessarily some approximation made and some choice of what we consider relevant we keep and other things we don't keep. And then you will see that it is not a full description, but perhaps still a useful description. And I chose 3 different topics: rocks, rivers and sand, and tried to show how a physicist approaches these kinds of complex systems, and hope to learn a little bit from this. So, yeah, okay, very good. Is it good? Can you hear me? Okay, good. Okay, so I will start by explaining in a little bit more detail what is meant by modeling complex systems with simple models. And it's an important point because sometimes people make a joke about this and say that your models are too simple and they cannot describe the complex system. And we start by saying that yes, of course they don't describe the complex system, but is this modeling still useful? That's what I'll try to answer. And then I will give 3 examples. Each of them is sort of selected in some way: fractured solids and river networks and sand piles. They are chosen from physics, roughly from my own work. But as you can see, they are actually somewhat different to begin with. But some similarities exist, and that I will try to explain and give some summary and concluding remarks at the end. And I am happy to, if you interrupt me, I am happy to be interrupted and explain some point if I am missing it. Okay. So, this is the preamble, this is what I am trying to explain my outlook on these things. So, the range of phenomena which physicists study is very big. There are distances which are 10 to the power minus 35, it should be above, meters Planck scale, and to 10 to the power 27 meters, which is the size of the universe, and time scales are 10 to the power minus 43 seconds to billions of years. And so, quite often in physics, people study these very big and very small, cosmology and quantum gravity. Okay, so those are the 2 ends of the things which are very sort of glamorous topics to study in physics. But my outlook is that while study of things very small and very large is also interesting, many interesting not so well understood phenomena also occur at human length scales. So, I will discuss problems which are closer to your everyday life and do not involve these very, very tiny things or very, very big things which are hard to really imagine. So, my aim will be to illustrate how simple models can help understand some of these rather very complex systems. Okay, okay, so we start with these fractured solids. This is a picture of cracks of patterns in mud, Kutch region. And can we, you see this picture, you have seen this stuff in real life, in every day. What can we say about this stuff? Is there anything to say or understand there? That is the first question. And I think the picture kind of explains to you already. We are trying to explain why this thing looks like this. As soon as you see this, you know that this is fractured mud, right? How do you recognize that this is fractured mud and not something else? What are the common features? If I take another picture, it will look different, but there are some common features. Can we identify them? Can we characterize them? Can we explain them? Okay. So this is a different problem. Is the catchment area of Ganga. Sorry, can I? Yeah, okay. So this is the catchment area of Ganga river and major tributaries. And there is a river, but a lot of rain goes into the river from other tributaries. And so the whole region, the water which comes as rain goes through into this river system, and that's called a river basin. And we don't want to understand one river, we want to understand the river system, river and all its tributaries, and can we understand them. And this is the third problem I will study, which is sand dunes. And what's there to understand about this? And why do we consider it complex even? It is not as complex as the human brain, but it is complex enough for me. Okay, and I will explain what is meant by complex enough for me here. Okay, so we start with this emergence in self-organization. These are the keywords. And this is a physicist's view of the world. So a lot of stuff is there which is also complex, we are not discussing, but we are discussing some part of the stuff with which we can understand a bit better. And I start with this Feynman lectures in physics volume 1, lecture 1. It is the, I don't know how many of you have actually seen this book. You should read it, it's a pleasure to read, and you will enjoy reading it, and you will learn many new things which you didn't think of in the first place in simple language. Anyway, it starts by saying that all things are made up of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart and repelling when squeezed into one another. Okay? And he says that if there was only one sentence which you were allowed to store, to save into future generations and nothing else, what sentence will that be? And he says this is the sentence. In this single sentence you can capture as much as you can of physics or our understanding through physics as you can in one sentence. Of course you cannot really capture everything, but this sentence says more than some other alternate sentence you could think about. Okay? And so you can ask, what other sentence could I have written? And then you will realize that perhaps Feynman was right and wise in selecting this sentence rather than saying that the cosmos started with a big bang, or the atoms are made up of electrons or something, right? Okay, so anyway, you start with atoms. From these atoms, one builds larger structures, molecules, that's called, that is studied in chemistry. And macromolecules like DNA, those are studied in biology. And then you can make living cells. Actually, this one is called biochemistry generally. And you can sell living cells, animals, societies. So that is biology and sociology. I think psychology comes in between at the level of animals. Because I think a whole society, can you have a psychology for a nation? Not sure, but you can think about it. Maybe some concepts of psychology are applicable at the level of a nation, maybe not. Maybe some concepts are applicable, but they are not called psychology. Anyway, you think about it. Some people actually say that there is a national character. Germans are some type of people, and Hindus are some other type of people, and so on and so forth. Is it true? How true is it? Can we think about it? That's a kind of question. Anyway, that's not my topic here, but I am just trying to get you to think about the problem in a new way. So, as we go from physics, which deals with atoms, to molecules and macromolecules, we are increasing in complexity. And we go from things like physics to chemistry to biology, psychology, sociology, ecology in higher level of organization. Okay? So, this word, say emergence in self-organization, there is a very famous slogan which was given by P.W. Anderson, which says more is different. If you take more of same thing, it doesn't behave just like an ensemble. Sometimes it picks up new characteristics. Okay? So, another way of saying the same thing is sum is bigger than, the whole is bigger than the sum of its parts. Okay? At each higher level of organization, new features emerge, which were not there in the beginning. That's called emergence. And from chemistry to biology, in chemistry there are molecules, in biology there are animals. Animals have some extra features which are more than just collections of molecules. Like they have a desire to live. I don't know if you can say that a molecule of water wants to live longer, it lives, but it doesn't have a desire to live. But animals, I think, can be said to have a desire to live. Sociology, there are groups of people who behave in one way, and there is class struggle and stuff like that. These are new concepts. The concept of a class struggle comes only when you start thinking of a society. There is no class struggle at the level of an individual, right? And sometimes, in order to discuss sociology, you will have to introduce concepts like class struggle. I am not saying that the Marxist way of thinking is correct or wrong, that's not the point, but it introduces this new idea which was not possible in the previous sense. So, this is called an emergent notion or emergent property. The class struggle is an emergent property. Okay? And so, there are these things like life, which of course is biology, and as I was saying that animals have life, and life has some features which are not present at the molecular level, DNA level even, which is things like desire to live or aim of life even, like people want to do something in their life or some such thing. That hydrogen atom or water molecule doesn't have any such aim of life, no? Okay, love. If you take small animals like worms, I don't think you can have a notion of love in worms. If you want to use that word, you can use it, but I think it is not reasonable to think of worms loving each other, really. But in higher animals, there is a notion of love you can understand, like you have birds and they have mates and they live together, they raise children together or some such thing, and I can identify that as what we call love, and it is a similar notion to love between humans. I mean, I am extending. So, maybe the birds also love, but worms don't love. Okay? And the culture is even a higher level concept than love, because culture requires not 2 people, but 2,000 people. If you don't have 2,000 people, you don't have a notion of culture. Okay? You can, I'm just trying to explain the meaning of the word culture. For me, what it means, maybe you have read it before, you understand something by it, but let us see. Can we say that group of cats have a culture? Cats, they don't live in a society. Usually they are kind of, okay, maybe they live in groups of 3 or 5, but they don't have a culture, and the culture doesn't evolve in time. So I'm just explaining this idea that as you go to higher levels, you get new features which were not present at lower level. So it's difficult to speak of culture in the case of birds. I think they have some songs or something, but they don't really have a culture. And for human beings, you can not talk about us without invoking culture at some level. And all these, in order to go from here to here, some organization is involved. And this organization doesn't come from outside, it is self-organized. And that is called self-organization. Nobody outside says, do this, do this, do this. They do it themselves. Okay? So now I come to my subject, which is my background. As a student, I studied statistical physics. And it is the study of properties of systems. It started with gases, molecules made up, a box full of molecules. Then you can sometimes determine the properties of the gas from the properties of the molecules. That was the beginning of statistical physics. And in general, statistical physics is the study of properties of a system having many interacting parts. And we are saying now that maybe if you take statistical physics, you can understand all these other levels of complex systems because they are made up of many interacting parts. And of course, they don't look like gases, but some ways of understanding many interacting systems in the case of gases can also be used in understanding higher levels of these complex systems. Okay. Okay, so this is the next point I want to make. It is the importance of simple models. So I start with this quotation of Einstein. It says that make things as simple as possible, but not simpler. And I believe that this is actually not correct. It is wrong. And in some cases, you have to make the problem simpler to make it understandable. If you take very complex systems, there is no way to understand them in full gory detail. And so you have to make them simpler. And so Einstein perhaps was okay when he was describing hydrogen molecule. It is not possible to take that philosophy and extend it to trying to describe the behavior of an ant even. Okay? In all detail, you have to simplify. Let me give another example which is useful. So suppose you are a doctor and a person comes to you and he says, I have a stomachache. Then you have to, you ask him, what did you eat? And he says, I ate this. And you say, take these 2 pills and go home and you will be okay. You don't ask, what is how many brothers you have, how many sisters you have, what is your father's name, what is your caste, and all these kinds of things. They are not important detail. Okay? A full description of the patient will involve all these details. We don't want the full information. We want only some relevant information. So finding out what is relevant is something which you have to learn. You have to realize that I don't need to know what color of shirt he is wearing in order to decide what medicine I should prescribe. Right? So it says deliberately ignore many details. Ignoring unimportant details is the core of understanding. To realize what is unimportant, you have to, that is understanding. And for better understanding, take no account of less important details. So initially you ignore all details, but sometimes details matter. Then you can take care of them systematically. In the beginning I said, I don't need to know your father's name. But if it is some complicated genetic disease, I might need to know if his father also had it or some such thing. So at some stage, it may be important to know a little bit about the father. That is called systematically increasing our knowledge. The simple models are not enough. Sometimes you need to go beyond them, but that we will do later. First you understand the simple model, then you can add complex details. Okay, so I will illustrate this idea with some examples. So we start with simple models, and if necessary, we make them more complicated later. Okay, so I will start with one example. Out of the three, this is the first one, fragmentation process. So a lot of work in this area in general for fragmenting processes, mainly from engineering perspective, and many industrial processes like mining, milling, involve breaking large blocks of matter into small pieces. You have to take a big rock and make it into small parts. A lot of energy goes into making these pieces smaller. Or we may want to avoid breakage. Sometimes we want to break, sometimes we don't want to break. So if you have cement, you build a house, you don't want it to break down, no? So we want to avoid breakage. Or airplanes, the wings shouldn't come off. So this is called strength of materials. In order to understand strength of materials, you have to avoid breakdown. And there are things like higher scale. This was, at the level of rocks and cement. This is geophysics, earthquakes. The whole earth may be sometime breaking, and you want to avoid the breakage. No, you cannot do it. Earth wants to break, it will break. You cannot stop it. But you might still be able to mitigate the effect of earthquakes if you understand the process of how earth breaks better. Okay? And there are other environmental studies, erosion of rocks, polar ice melting, etc., which are important. And all of these involve these fragmentation processes in general. And if we understand one of them, maybe we understand a little bit about the other one. See, they are very different. Some of them are very different from each other, but understanding one may help in understanding the other. So the theoretical work has generally focused on determining fragmentation size distribution. So this is a new concept. It says take a big rock, break it into small parts by some process, which is some hammering or something. When you do this process, or explosion, they take something, explode, and it breaks into small parts. I want to determine what is the size distribution of parts. Some are big parts, some are small parts. And so it turns out that sometimes this kind of size distribution is independent of material details. You take one type of rock, another type of rock, same kind of hammering will give you same type of distribution of parts, at least for a class of processing protocols. So we want to understand this, for example. So I'm making a particular choice. I'm saying, okay, let me look at this fragment size distribution of fragmentation processes. Okay? So this, our work was started by some paper which appeared in this Nature Geoscience, and it talks of termini of calving glaciers as self-organized critical systems. So there are these glaciers, big pieces of ice, and they break like that, cracks appear, and the cracks, the whole glacier breaks up into parts, and the part goes into the sea, and in the sea it melts faster. And then, if lots of glaciers in the polar ice cap melt, then it raises the sea level, and that is a big question. So people have asked that at what rate is the ice melting? Can we estimate this from data or some such thing? And so in any case, it is useful to know how does the ice break. It's an example of an application. I'm studying the distribution of sizes, but maybe it is applicable to the case of some processes like glaciers breaking, and it's called calving because you say this is a big cow and that one is a small calf. Okay. Okay, so now I will take a particular model, I will define, I gave you the process is the glacier melting. But now we make a model of this process, and it's based on the picture described before. This is also a model, this is not the real ice, but it's a computer model. And what they did was they put something and the computer makes this picture. And then you look at this picture and try to understand it. Okay. So we make a simpler picture. And we start with something like this. It is called a square grid. You can actually see the grid, which is a light gray color. And so there is a sheet of ice, and a crack is described by these red lines. Okay? And on the left side is the sea, on the right side is ice, and cracks develop on the left side and they propagate to the right. As they propagate to the right, they can either go up or down. So there is a little bit of diffusion. They don't go in a straight line, they go in a slightly random way. And sometimes they can split. One crack can become two cracks. And sometimes they can merge. Two cracks can become one crack. If they come together, they become one crack. That's all we are taking into account. We are not taking into account any other detail of this system. Just using this much input, can I say something about this process? That's the question. And so this is the model. The model says that there is a crack. It can, with some probability, it can go to the left. With some probability, it can go to the right. And with some probability, it can split into two. That's all we will do. And if two come together, they merge and act like one crack. So after that, it behaves like one crack. It can go left or right, or it can split again. Okay. So I already said, cracks are initiated on the left and move to the right with constant velocity, random transverse displacement, two cracks merge. So this model was studied earlier by Ben Abraham et al. And Krebs et al., but as a model of aggregation, disaggregation. So they've studied, they think of a model on a line, and particles can move around and they can join and they can become bigger. But they were not looking it as a crack in a two-dimensional system. So the same model can also describe a two-dimensional process, which is what we are doing now. And this is a bigger picture of the same. You make a model and you can make a bigger picture. So this is the result of a simulation of a model on a lattice of size 80 evolved for 150 time steps. And there is a particular choice of splitting rate I have taken. Okay, and then you can look at this picture and you can see that there are fragments. The whole process goes and the cracks keep on going, but behind, once they have merged, they leave behind a fragment. And the size of fragments can be very small or very big. There is a big distribution of size of fragments. Can I understand this fragment size distribution in this simple model? And I am saying that the answer is not immediately clear and obvious, and it requires understanding and some experience with the techniques of statistical physics to be able to answer this question. That is the use of this kind of a theory. It gives us tools to handle such questions. Okay. Yes, sir. Yes. Yeah. In this simple model, we have not worried about it. You can add that as the complication, extra detail next time. Right now, the sea is here and the cracks go roughly perpendicular to the boundary between the sea and ice. Okay, in this simple model. One can add complications, but I am not doing it. Okay, so the steady state of fragment size distribution, rate satisfied detail, this is a technical detail, but you can tell what is the steady state of this system. And it's described by a very simple Hamiltonian, which is independent particles with a chemical potential. That's a detail, you don't know what is chemical potential, don't worry. We will not need it to understand the stuff. And each fragment is a region bounded by two bias directed workers. So this is the point I would like to say. If you look at a fragment, this one, what is it? There are two workers who do random work, and once they come together, they become a fragment, and the size of fragment is just behavior of these two workers. What happens to other people doesn't matter. What other workers are doing, I don't care. In this problem, the boundaries are just two workers, and so I reduce the problem to that of two workers. Okay, many results. So this problem has been studied for a long time, 50 years. and it's called area under Brownian bridge or some such thing. Many results are known. So fragment size distribution, this is the log of the probability of the size, and this is the log of the size, and there is a distribution like that. And it is known that if you have some lambda, then the probability of A looks like lambda to the power 4 something, and this function G looks like something for small x and something for large x. All these details are there. I can derive them. But right now I will not do it here, because it will require some time, and that is not my present aim. So I am saying that you can actually calculate this curve from first principles in some scaling limit, it is called. Okay. Okay, so summary of this fragmentation size modeling. I discussed a simple model of fragmentation of propagating branches, merging cracks, and here the relative frequencies of different fragments can be exactly determined. Okay, qualitative agreement with observations of calving termini of glaciers. So now I can go back and see, okay, you did all this study of this particular thing, is it any use? So this is, this is the picture of the model, and this is the picture of the sort of more complicated model or the real thing, if you like. And is there any thing to be, is there any common feature between the two? And I would say at the picture level they look the same to me, and that is the explanation, that is the advantage of the model, is that some features of the actual complicated system can be explained by this simple model. Yes, sir. Sorry, can you say it louder?
Sir, as Prathu sir highlighted that, this model is moving in different angles in an uneven manner. But the model that you showed from Avraham, that's moving in a particular proportion of 1 minus lambda by 2 or either lambda. So there is a uniformity in there, but in this case, I don't see any uniformity. So is that relevant in this case?
Yeah. So this problem is more complicated. So you can ask that, is the simpler model still useful, or did I make unnecessary simplification which makes my model irrelevant? And I am making the point that it was not irrelevant, it is actually a useful simplification. Sometimes it is better to make a simpler understandable model than an understandable complicated model. This point is not realized by everybody. In fact, I know some very wise people who have said the opposite. I will tell you the opposite. They said that, look, there is one model A, one model B. Model A has 5 parameters, it fits the data perfectly, and model B has 1 parameter and it doesn't fit it perfectly. So A is better than B. And I would say no, it is not obviously true. Okay, that is my philosophy. Let's go on. We can discuss this later in the discussion section. Okay, so now I come to river networks. It's a different problem. And rivers have been the cradles of human civilization and very important in determining our environment. Civilization has evolved around banks of rivers. Human civilization has often evolved around banks of rivers, Nile River, Ganga River. Okay, so this picture we have already shown before. This is a Sindhu River basin, and you can see the western India, sort of old India, not present India, but Afghanistan included, Sindhu River basin. And this is Amazon River basin, and you can see large number of rivers which go into it. It encompasses almost all of the continent of South America, Brazil actually, but okay, half it's a good part of the continent. No, I am trying to emphasize the size of the object we are trying to study, and people don't always appreciate this point. And this one is the next one, it's America, and you can see almost all of the continental United States is the basin of the river Missouri, Mississippi River, Mississippi-Missouri कहते हैं उसको, Mississippi River basin. And all these tiny rivers join into this Mississippi River. It's a big river. somehow it is not philosophically as important as the Ganga river, but it is perhaps equally important. Geographically, it is equally important. Okay. So modeling rivers, can we predict? So I showed you all these pictures of rivers. Can we understand anything about rivers? Can we predict the structure of the network from the physics and geology of the region involved? So if I give you the landscape of America and the rocks, this type of rock is here, this type of rock is there, this height is here, can we tell what will be the river network like? So actually the river network evolves in time. The rivers move, and so it changes with time. And water flow transports sand, which changes the land elevation, which changes the river flow. And so you should not ask about the river network now, but you should ask for what could it have been. It could have different shapes. What are the different shapes possible? What was it like some time ago? What it could have been? Okay? So modify the question. I don't want to ask that question. I want to ask a different question. And this different question is the following. Are there some general properties of networks independent of details of geography? Same for all river basins. Okay, so I go back. I have this picture and this picture and this picture. They are all different, but are they same in some way? What is the common feature between all these different pictures? Can we try to understand that point? What is the common feature of all these river networks? Okay. And so now I give you some hydrology. People have studied river networks for a long time. And these people are called geologists and hydrologists. And more generally, these are called drainage networks or supply networks. So drainage network is something in which water comes and it has to go into the sea and it drains out. And river streams join and they go out together. There is a different thing called supply network, in which some big company like Coca-Cola company makes up lots of Coca-Cola. For the moment we are imagining it is made at one place and then it has to distribute it to a whole area. Or a post, there is a lot of mail comes into one central office and postman has to deliver it. Or let us say, in the old days, there was air mail, and air mail comes into the airport, it has to go all over the country. So what does it do? It divides into parts. Some part goes to east, some part goes to north, then the part divides further and so on and so forth, right? So you have to make up these supply networks. So can we understand them? So a network may consist of thousands of rivers. And so, some notions of statistical physics are likely to be useful. So very interesting idea, which I can explain in a few minutes, is called the Strahler rank of a river. Okay, so I will explain. So you have a river network, let us say like this. So we identify small rivers and big rivers. Small rivers are given lower rank and big rivers are given a bigger rank. That is the basic idea. Okay, and so what one says is that if there is a nala which has outflow which is very small, like less than 100 liters per day, then I will not count it, I will not worry about it because it becomes too complicated. So you put a lower threshold on the kind of rivers you will worry about. Smaller rivers we don't count. Then I have drawn this network. If I took all size, then even this will be more rivers to be added. But at this scale I have some river network. There are rivers which start. All the rivers which start from some point are called rivers of rank 1. When two rivers of rank 1 join, it is called a river of rank 2, it's a bigger river. If a river of rank 2 joins with a river of rank 1, it remains the river of the same rank. But if two rivers of rank 2 join, it becomes a river of rank 3, and so on. So if you have a big river like Ganga and a tiny nala head comes, it doesn't change the rank of the river. But if two rivers of equal rank join, then it forms a river of a bigger rank. That is the Strahler rank of a river. Okay? So many observed regularities in river network, people observed by just phenomenologically. One is called Horton's law. It says number of streams of rank R divided by number of streams of rank R plus 1 is a constant. Across different river networks is about 4. Why should it be? Can I explain this? There is another law called Heck's law. It says length of the longest upstream river. So you stand at a point and try to go upstream on the river. So you can go this way or you can go that way. You go along the way which is the longest. So it's called the length of the longest upstream river from that point. And there is another thing which is called how much water is flowing downhill from here. That is called the area of the catchment basin of that point. And there is a statement that this length of the longest segment goes as area of the catchment to the power A. Sorry for these typo errors which comes because of some complication, but A is about 0.6. And can we, so this is an observational law, this is an observational law. Can we have a theory which explains these laws? Can we understand these laws from first principles? That's what we try to do. So can we derive these laws from more basic principles? That's the aim. And so there is a model due to Scheidegger of a river network, which I will give you here. So he said that take a plane and imagine that rain can fall on this plane roughly at a constant rate. So at each point, firstly you divide the plane into grid. So a whole region is called a grid, square is replaced by a point, and all the water falling into this square goes into this point, and from this point it flows downhill either to the left or to the right, and from every point some water flows downhill. But water can also come from above, and then this water, at this point some water comes from here, some water comes from here. There is 1 unit of water which is added from the local rainfall and it goes down. And it keeps on going like this. You do this everywhere. Every point you decide which way down it will go. That is fixed in space, and it is randomly fixed in space. And you get a network. And it's a, so this is called a model of river network. And the claim is that you make such a model, whatever choices you make, it will look roughly the same, and it will roughly look like the real geographical river networks. Okay, so let us see if I can go back, or I will avoid going back and I'll just go forward. Yeah, so the Scheidegger model is a directed random spanning. So this model is called a random spanning tree because it's a graph which takes all the sides, and in the end they all get connected, so it's called a tree graph. And then you can reduce the properties of these graphs, and many properties can be deduced. So for example, fractional number of sites with outflow f goes like f to the power minus 4 by 3. And fractional number of sites with longest upstream goes like L to the power minus 3 by 2. And Horton and Heck laws are obeyed in this random river network. So I say that of course there is this phenomenological law you have seen, Horton law, Heck's law, but they can be explained by this simple model. So this simple model has the usefulness of understanding where the Horton law comes from. And I simplified, I got rid of all kinds of detail, and it still keep the basic property that there is a scaling relation between area and length of river. Okay, the summary of discussion on river networks. Simple model of river networks is the Scheidegger model. In this model, catchment basins are staircase polygons, and so if you look at the this point, what is the water coming into this point? All these points which come from all these points are flowing into this. So at this point, there is a catchment basin. If you look at the catchment basin, it has this shape. It is called staircase polygon because it's made up of 2 staircase-like lines. And people have studied the properties of these staircase polygons before, and so I can deduce all those laws. Okay? So now comes the question. Is the Scheidegger model a good model of real river networks? You can ask this question, and you can ask honestly, don't take my word for it, does this model look like these pictures? And somebody will say, no, it doesn't look like it. But somebody will actually say, yes, it looks like it in some crucial ways, not in every way, but in some important ways it actually looks like that one. And that's what we are trying to describe. That's what this simple model does. Okay, very good. So it says in this yellow color, yes, for some properties, not everything. There are lots of other properties of rivers which I didn't take into account, which is called the width of the river. Sometimes it's wider, sometimes it's narrower, and other things. You can add those details. Those are the, I said a simple model. You can take more details into account to make a slightly more detailed model. But you will still ignore some things. Okay, so finally, I will discuss the third model we want to discuss. It's called the sand pile model. So in 87, Bach et al. Noted that many natural systems appear to have long-range correlations over a wide range of control parameters. And they made the bold proposal that relaxation dynamics of many open non-equilibrium systems is such that it drives the system to the edge of stability and keeps it there. So this was called self-organized criticality. And they gave examples of earthquake extinctions and Barkhausen noise and all kinds of stuff. And the simple example they gave is of a sand pile. So they said they take dry sand, pour it on a table, you make a pile like this. This pile, you make it again. It roughly has an angle with the horizontal. All the surfaces have an angle which is called the angle of repose. It's the same. If you make the pile again, you will get the same angle. It doesn't depend on how big the pile is. Okay, the angle with the horizontal is called the angle of repose, and it's identified at the edge of stability. If the pile is of smaller angle, then you add something, it stays there. If you make a bigger angle, then it will be unstable, and adding a little bit, it will just crash and you will cause a big avalanche. So if you just add at random, the natural dynamics of the system makes it such that the pile is formed at the edge of stability. The angle will be the angle of repose. So the system organizes itself to be at the critical point. This was the idea. Okay. And if you look at the outflow of sand, sometimes it's very small, sometimes there is nothing, but sometimes there are very big avalanches. And the size distribution of these avalanches is big. Encompasses several orders of magnitude. They can differ by 10 to the power 4 or 5. And so here is a simple model of sand pile. It's called wooden blocks on a staircase. So you take staircase, and there is these are wooden blocks, and there is a child sitting on top. He plays with these wooden blocks by dropping them on the top layer. But if two blocks come on top of each other, then they become unstable and they go down to the next layer into two sides below. Then there might be something below, then this thing will also topple and to go down below. So in the steady state, the height of the pile here can be only one at each place. You cannot have two things on top of each other. That's my model. Okay, so this is the definition of the model. Okay, sorry. It came. I was worried that the picture didn't appear. So there is a pile here. I add something, it becomes 2. Then this 2 topples, and one particle will come here, one will come here. These will become 2. Then this will topple, one will come here, one will come here. And this will become, and from 1 will come here, this will become 2, this will become 3. But 2 particles will drop down, and now the toppling stops. So given some configuration, you add something, eventually it stops. Sometimes some grains will leave the pile. If they go below the bottom, they leave the system. Okay, and then you keep on doing this, and you can form a pile, you can form avalanches. They have distribution of sizes, which you can calculate theoretically. Okay, and then so the key property here is that if you look at a avalanche caused in this model, you will find that okay, this particle toppled here, this toppled here, this toppled here, and this is the set of toppled sides, and the boundary forms a staircase polygon. So, same mathematical object comes up in these different models we studied. Okay. Of course, the models were chosen so that the same thing appears. I am not saying that everything in the world can be reduced to staircase polygons, but I am saying that different physical systems, river networks and sand piles, can be described by the same mathematical structure called staircase polygons. And so you can show that probability of stopping S topplings goes like S to the power minus 4 by 3, probability of duration T goes like T to the power minus 3 by 2. And so this is the summary of my talk. 3 different models of ice sheet breaking, river networks and sand piles. And in each case, we reduce the problem to the study of staircase polygons and characterizing the resulting stochastic geometrical structures. And staircase polygons are not necessary requirements. Some results may be extended to other shapes, lattices, even to higher dimensions. Okay? And more detailed modeling is necessary for comparison with field data. So I am saying that we made up this simple model, but if it turns out that this model does not describe the real system very well, I am willing to modify the model and have a more complicated model. It is not the end of the world, but it is a useful starting point to start with simple models. Okay? And I think that is the end of this presentation. There are some references. For the fragmenting sheet, you can look up this one. And this whole talk is somewhat similar to an article I wrote for simple models of complex systems. It is downloaded free, you can find more details there. And there is also an article I wrote for Physica A for self-organized criticality. It is a review article. It has more details, but you may not want to read all of it. Okay? And that is the end. Thank you. You have to give him the mic.
Oh, that's fancy. Hello. Thank you so much, Dr. Dhar. So my question is that all of those 3 models you presented are kind of similar to each other based on some kind of branching. Some models include the kind of merging, etc. So are they fundamentally related to each other, or are they different?
They are mathematically equivalent. They are the same model in mathematical structure, but in application they are very distinct. If I show you river network and I show you sand dunes, you may not see any connection between them. And the utility of these simple models is that it helps you identify connections between seemingly disparate objects.
Good afternoon, sir. Sir, as you said, it delves into the disparity of the objects, but one thing that was common which I observed is those were all microscopic studies of those branches. It was not taking the Mississippi Plain or any sand pile at its largest extent, it was just taking a branch of it. So in that case, as you said, P.W. Anderson says more is different. So if we apply that theory, does it nullifies it? Like, does this modeling becomes nullified? And adding on to that, does that also implies that on a Planck scale level, when we are studying universe, it's becoming more expansive. But universe in its nature remains quantum and non-linear. The expansion remains non-linear. So how can we define it or understand it through that same relevance of 1 minus lambda by 2 or lambda?
Okay. Our aim at this level was to understand the properties of the sand pile in terms of the properties of the sand grain. It only applies to the fact that lots of sand grains are together. Can we tell what happens to a sand pile when I know how the grains behave? So I give you the microscopic interaction between grains, and I can tell you the macroscopic properties of the pile. If this pile is part of an even bigger thing with other things that we are not discussing, that is a limited aim. But at that limited aim, we are able to work.
Sir, I had a question. So, I know this is primarily about theoretical physics and everything.
Sorry?
I know primarily you're a specialist in theoretical physics, but I had a question regarding how it ties to, like, as he said, the universe in general is quantum and non-linear, right? So, I'm not sure which exact experiment it is, but there's an experiment in quantum physics where it shows that when particles are being watched, they change their behavior, right? So when we take into consideration the paper you showed of the Termina glacial breaks and their splitting and everything, right? So on a smaller, minute level, like the more complex level, does this apply to them as well? Because if they are aware of some entity or anything above that's keeping an eye on them, maybe on some level they also change their behavior?
Okay, let me answer this question because it's a common difficulty with many students. So the point is this: when I am trying to understand sand piles, I don't need to know what happens to the universe. The part I said about forgetting about unimportant details also says I don't need to know how galaxies are expanding. If you want to have a single answer for all the possible questions you can ask, how is the universe expanding, where job I'll get next after I finish my work, and how does this quantum mechanical particle behave when you look at it, you don't look at it. These are very different questions, and it is not reasonable to expect a single theory to answer all of them. The theory we discussed here only answers, okay, you take a sand pile, you take a grain, how will the pile behave based on the properties of the grain? What happens to a quantum mechanical system under observation? It's not addressing that question at all. It's a totally different question, it has a different explanation. Single explanation for everything in the world is not possible. There is no theory of everything. If somebody says that we are studying some such thing, I think they are hoodwinking you. This you can realize, the people who say this are not stupid people, they also know this. And they actually, the next sentence they say, well, when we say everything, we mean this. And so watch out for this. Okay.
Hello sir, I'm Aditya Dhani. So as you mentioned, like atoms we have, but at a higher level we are humans. Atoms don't have that capacity to think, but we do have. So how we can say that microscopic judgments can lead to higher macroscopic things? Like how can we judge the universe with molecules? As you said, they have certain different characteristics that develop when they come together. So how can we just do it with a single atom and describe the entire universe?
Okay, so what I said was that the description of the world describes at different levels. You can work at the atomic level, you can work at this level, this level, this level, but you can also make bridges between levels. From the description of molecules, I can try to discuss what happens when 50,000 molecules come together, right? That is going from one atomic level to a description at the level of drops of liquid. We are confining ourselves just now to this level, but it turns out that if you have lots of cells and you know the behavior of one cell, I want to tell what is the behavior of a group of cells. Same techniques can be used to discuss some parts of this behavior. Okay, so yeah, so those words are common. The details of description are not the same, but some philosophy of this approach is applicable in other cases, in stock markets, in earthquakes, or whatever it is. And you can go from one level to the next level. I don't have a theory which allows you to go to jump to two levels in one go. Okay, maybe you can develop such a theory. You are welcome to try.
something that's very scientifically driven or has to be filled with very specific terms?
Can you sort of say it louder?
Does the theory that you're asking us to propose have to be anything that's scientific? Because I think at the end of the day, for me, it's just having an inherent belief in something.
Sorry,
So
at the end of the day?
it's just having an inherent belief in something. Like even when you, the most like interesting thing for me, what you were talking throughout the PPT, was the self-organization part. Simply because how molecules at a very microscopic levels can come together, and as you mentioned before, like how they like turn into something macroscopic and something that we inherently can see in the world, right? So all these complex systems that come together, they all have like a simple molecular structure which we need to understand, right? And for all theories, I think the base of most of them, even though it's not very scientific and it's rather philosophical, it's just to have an inherent, very like determined will and belief in it, to be able to comprehend it and to be able to understand it. It's, the answer is not scientific at all, I understand. It's just what I think personally.
No, I understand the point. What I will say is that I've tried to emphasize that what we are doing is not explain everything in the world, but some parts of it. So I can explain how the cell works based on how the molecules in the cell work, if I am lucky. I don't want to be able to explain in the same theory how a human being will work because I know how the cell works. Okay? So simple explanations for everything possible are not possible, should not be tried. You should not try to have a single theory which will explain everything in the world, and one step at a time is what I will suggest, is what we are trying to do. We go from one, we make a connection between one level to the next level. That's the best I can hope to do. Right now I am not aiming for more. Okay? Okay.
Here's some more.
Thank you, sir, for engaging with our audience. And I hope someone can get with a theory of everything maybe from here. So moving forward, I'd like to thank everyone for your time and for your patience. So we shall now break for lunch. Lunch will be served for our guests and the conference participants at the banquet hall. So I would request you to please kindly move towards the banquet hall. The paper presentation sessions will resume sharply at 1:45 in the respective rooms in the management block. Thank you, everyone. Before we formally begin the valedictory session, I would request everyone to join us in a moment of silence. Thank you, everyone. Good afternoon, everyone, and a very warm welcome to the valedictory session of our conference. Over the past 2 days, the conference has been a truly stimulating intellectual experience, marked by insightful keynote address, thought-provoking paper presentation, and rigorous academic discussions. To formally commence the valedictory session, it is my privilege to invite Dr. David Joseph, Department Coordinator for Department of Commerce at Christ University, Pune Lavasa Campus, and a key member of the organizing committee. An assistant professor and an active researcher, his work focuses on fintech, financial capability, and the ways technology shapes financial decision-making and behavior. Deeply engaged in research and curriculum development, he is committed to preparing learners for the evolving demands of the financial sector. Sir, I request you to kindly take the stage and deliver the welcome address.
distinguished guests, esteemed general chairs, renowned speakers, fellow researchers, faculty members, and my dear students. A very good afternoon to all of you. Good afternoon. Yes. As we draw the curtains on these 2 days of intensive intellectual conference, it is my absolute honor to welcome you to the valedictory ceremony of the International Conference on Complex System Modeling, Analysis and Applications, CSMA 2026. This conference was organized through a vibrant collaboration between Christ deemed to be University, Pune Lavasa Campus, and Binghamton University, the State University of New York, and graciously sponsored by the ANRF Foundation. This conference has been a true testament to the power of the global academic synergy. We are privileged to have with us our General Chair, Dr. Father Lijo Thomas, Dean and Director in absentia, and General Co-Chairs, Father Justin P. Varghese, Academic Coordinator, Dr. Jibril Jose and Dr. Parameshwarans, Associate Deans, whose vision continues to guide this institution toward research excellence. A conference is only as strong as technological rigor. We welcome our technical chair, Dr. Hiroki Sayama, Distinguished Professor from Binghamton University, Dr. Preeti Hen, Head Center for Research, whose dedication ensured a curriculum of the highest standard. A special word of gratitude and welcome to the ceremony our keynote speakers, Dr. Anirban Chakraborti and Dr. Deepak Dhar, for illuminating our path with their profound insights and the intricacies of the complex systems. I also extend a welcome to the HOD, Dr. Manjari Sharma, other HODs from other department, faculty members, and my dear students to the valedictory ceremony. Over the last 2 days, CSMA 2026 has saved a bridge between the hills of Lavasa and the halls of New York. In this hybrid mode, we successfully hosted the presentation of 30 scholarly papers, each contributing a unique thread to the complex modeling. From deep dive analysis to innovative applications, these presentations have challenged our perception and opened new ideas to the future of the complex model system. To the researchers and the organizing committee members, your hard work is the heartbeat of this conference. As we move to the final proceedings of this conference, let us celebrate the friendship as well as the ideas sparked through this conference. Once again, a warm welcome to all of you to the valedictory ceremony of the conference. Thank you.
Thank you, sir, for welcoming all our guests and participants. It is my honor now to invite our academic coordinator, Father Justin P. Varghese, to address the gathering. A senior academician and administrator, he has played a pivotal role in the campus academic and institutional growth, shaping its vision, strengthening governance, and fostering a culture of interdisciplinary teaching and research. His leadership reflects a deep commitment to holistic and value-based education, with a strong emphasis on experiential learning, ethical formation, sustainability, and social responsibility. As the General Co-Chair of CSMA 2026, he continues to guide and support the effective coordination and smooth conduct of the conference. Father, I request you to kindly take the stage and address the gathering.
Good afternoon, all. Esteemed guest, Dr. Deepak, Dr. Anirban, and Dr. Hiroki, respected faculty members, and my dear students and researchers. When we speak about complex systems, we always say the whole is greater than the sum of its parts. When I look at this conference also, I feel the same. The impact of this conference is about the wholehearted contribution of each one of you who are actively involved with. And I am just here to appreciate all the efforts, starting from our Binghamton University, the sponsors also along with them for this particular conference. Can we have a big round of applause for them for helping us out? And can I have all the organizing committee members standing wherever you are? Just stand. for the So really appreciate all the efforts. It's not an overnight event. You have been planning and you have been doing a lot of hard work into it. Put your heart and mind into it so that it will go smooth. So thank you so much and appreciate all your efforts that you have done towards the same. Thank you. Sit. Also, I would like to thank the faculty coordinators and who really guided them, and also all the people who presented the papers. Can we have a round of applause for all of them? So appreciating all the people who really worked hard for making this happen, and a special appreciation to the Department of Commerce altogether. The appreciation goes to each and every one of you for your active participation. Hope that each year we will have the growth that is being expected in terms of research, because you all know that each of the higher institution is really focusing on the research, and we started with our honors program where we will be having more focus into the research culture too. So I take this opportunity again to thank our esteemed guests who are here, Dr. Deepak and Dr. Anirban, and special thanks to Dr. Hiroki for traveling all the way and making it happen. Can we have a big round of applause from them too? Once again, I thank each one of you for all your efforts that you have made it for making this happen. Thank you. Have a great day.
Thank you, Father. Moving forward, now I would like to welcome our esteemed guest, Professor Hiroki Sayama, State University of New York Distinguished Professor at Binghamton University, USA, and the Technical Program Chair of CSMA 2026, a globally respected scholar in complex system science. He has played a pivotal role in guiding the academic direction of this conference. Sir, I kindly invite you on the stage to deliver the valedictory address.
I would like to first thank again all of the people who made this conference possible, including the organizing teams, Dr. Preeti, and also the faculty members, staff members, student members. So thank you so much for the amazing work. And also the authors and speakers, especially the esteemed keynote speakers, Dr. Dhar and Dr. Chakraborti. And then the reason why I traveled more than 36 hours, just to meet you two in person to take a selfie, I'm going to post to the social media. Thank you so much. I believe this time, this is the second time of the CSMA held here. And I clearly see that the people are now getting the idea of complex systems. That is reinforced and even strengthened by those two keynote speakers and talks. And many of the presentations I saw by students, researchers, PhD scholars, they are getting the idea. And this is very encouraging. And I believe that the next year we're going to have even more solid, larger conference focusing on complex systems. So we are already start discussing what we're going to do next year. So we want to invite everybody's participation, not just attending a session, but maybe as an author. And one final thing I want to mention is that this conference comes with the publications. So we publish a Scopus indexed open access journal edited by researchers in the Northeast region of United States. It's called the NEJCS, Northeast Journal of Complex Systems. And then many of the authors already submitted a final revised version of the papers for the proceedings. So please give us some time. Me and my staff members need to go through all the editorial details. So the paper will be published as they finalized, probably in the next several weeks, probably not several months, I hope, but the publication will be coming out. So once you see your papers published, please spread the word and invite other people to consider submitting their work to this conference. So that's the final advertisement, so to speak, that a little bit of contribution our university, Binghamton University, State University of New York, has been bringing to this community. Once again, thank you very much, everybody, everyone for contribution, and we hope to see you again next year.
Thank you, sir, for honoring us with your presence during this conference. Before we formally conclude this session, we would also love to hear from our participants. So I would request our participants to come and share their experience about the conference with us.
First of all, thank you for all the organizing team and also the organizing faculty. So it has been a privilege to be a participant. So I've been participating in CSMA conference. I was there last year, and I'm here this year as well. So one of the best things of this conference is to interact with the people who are best in this research area, complex system science. So also getting to know what are the various applications that are possible. So we have seen during the lecture by Professor Chakraborti and also Professor Sayama, so the range of applications that are possible through systems, complex system science field. So, and as always, Christ University has been a very hospitable place. So whether it is attending some lectures in Bangalore campus or in Pune campus, so it's always hospitable interacting with your faculty members here. So I would love to visit again, so if the conference is held next time. So thank you all. So thank you very much. So it has been a privilege attending this conference. Thank you.
A very good afternoon to one and all. I'm Rosalind. I presented here, and I come from a university, from a college where I teach, and majority of our students come from lower socio-economic backgrounds. And it's my honor and privilege to be with students where they have presented eminently in their own field. Something that is really missing in our education system at the moment is humanity, interdisciplinarity, and through this conference, that is what I learned from all the speakers, the organizing team, and I thank Christ University, Dr. Preeti, the entire faculty members, Dr. Anirban, the other speakers, Dr. Deepak, Dr. from Binghamton. So thank you so much for everything and helping us to grow more. We will carry the values ahead with us, and we will come back next year stronger as a team. And looking forward to meeting you all and bringing our faculty members also here so that we create a better tomorrow for our students. Thank you.
Thank you for sharing your valuable insights with us. To conclude today's session, I now invite Dr. Preeti N., the Technical Program Chair of CSMA 2026, to address the gathering and deliver the vote of thanks.
It is with profound gratitude and sincere appreciation that I propose the vote of thanks on the success of occasion of International Conference on Complex System Modeling, Analysis and Application CSMA 2026. At the outset, I express my deepest respect and gratitude to our Honorable Director, Father Lijo Thomas, for his visionary leadership and steadfast commitment to fostering a culture of research excellence at Christ deemed to be University, Pune Lavasa Campus. His guidance and encouragement continues to inspire academic innovation and global collaboration, whose constant support and institution direction have been instrumental in strengthening this international academic initiative. My sincere thanks to Father Justin P. Verghese for his academic guidance and continuous encouragement throughout the planning and execution of this conference. Thank you, Father. I gratefully acknowledge the valuable administrative support of our associate deans, whose coordination ensures the smooth conduct of this event. We are deeply honored by the gracious presence of our distinguished chief guest, whose eminent contribution to academia and society have elevated the stature of this conference. We are equally privileged to have been enriched by the keynote address of Padma Bhushan Awardee and INSA Distinguished Professor Dr. Deepak Dhar. Thank you, Professor. And Dr. Anirban Chakraborti, Professor at JNU and Fellow of the World Academic of Science. Thank you, Professor. Their scholarly insight and pioneering research have profoundly inspired participants and strengthened the intellectual framework of CSMA 2026. I extend sincere appreciation to Dr. Hiroki Sayama, Technical Program Chair, for his invaluable collaboration and academic leadership in shaping the scientific rigor and international appeal of this conference. Thank you, Professor. We are deeply indebted to our HOD, Dr. Manjari Sharma, for her invaluable guidance. Thank you, Dr. Manjari. We also owe a great deal of thanks to Ms. Priti Jain and Dr. Magesh Kumar, whose administrative excellence serve as the foundation of this event. Thank you very much. Our sincere thanks to Dr. Alvin Joseph from the Department of Data Science for his time and expertise, and to Dr. David Joseph for his constant encouragement. We also acknowledge the vital contribution of our teaching and non-teaching faculties. Thank you. A special mention to our students' lead, Sejal and Mritula, and the core committee of our students. Your energy and hard work were the driving force behind these proceedings. Without this collective effort, an event of this scale would not have been possible. Thank you, Sejal and Mritula especially. I convey my sincere gratitude to all the authors, presenters, delegates, and participants whose scholarly contribution and active engagement have made CSMA 2026 a meaningful and impactful academic gathering. May this collaborative spirit fostered through this conference continue to inspire research excellence, global partnership in the years to come. A special thanks to Dr. Hiroki Sayama for accepting for the next year conferences in Pune Lavasa Campus. Thank you very much, Professor. With gratitude and appreciation, I conclude this vote of thanks. Thank you and have a day good ahead. Thank you.
Thank you, ma'am, for summing up the entire event and thanking every person who has worked tirelessly for this conference. With this, we formally come to an end of today's session. But before that, I would please request everyone to kindly stand for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा। जनगण मंगलदायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।